Hi, so today we're going to talk about tectonics. And so this is the bigger picture aspect of structural geology, the regional scale patterns that we find in the rock record that tell us about how the Earth's surface has evolved over time. So we're going to start by drawing out the one of the main sort of tectonic features that occur called a sedimentary wedge. So sedimentary wedges are packages of sedimentary rock that develop along continental margins. And a good example being the modern Atlantic margin. So this is what the Atlantic margin looks like today. So inland, we have a fair amount of basement rocks, so high-grade rocks like the Manhattan schist. Granites. And then there's we call the platform, which is it's underlain by high-grade rocks, but it's a thin layer of sediments. So we call this the platform. And then back here, actually, we could put some more mountains. This area we call the shield. And there'll be some features here that involve unconformities and normal faults. Okay, so there's normal faults and these have layers of sedimentary rock in them. Let's do another one here. So these are old normal faults. You can see that the rock layers have been tilted. This is kind of like the Grand Canyon example. It features kind of like this. Okay, but below those, below those unconformities, it's this granitic stuff. So this is like continent. We could kind of show the thickness of continent would be thinning. So this would all be originally kind of rock that was what we call continental. So it wasn't formed in the ocean basin. And okay, so you go to the coast in the Atlantic, and so now we're going to show like the modern, okay, so here's the ocean. Here's the Atlantic Ocean. This is the water. And below water is a lot of sediment. You can imagine all the rivers coming off the continent have been depositing sedimentary layers for a long time. And they've piled up. And the thickness here can actually be pretty incredible. Something like 11 kilometers thick. pile of sediment. So this is what we call the sedimentary wedge. This is the sedimentary wedge. It's this just incredibly thick section of sedimentary rocks that occurs on the margins of continents. Okay. All right. So underneath, this is deposited on some older rocks, and eventually you get to a point where you no longer have rocks that started out as a continent. You've got ocean across. So we're going to put like magnetic stripes on the ocean floor. So, and if you go far enough out in the ocean, you get to the mid-ocean ridge. Right. So this is the place where new ocean crust is being created. Okay. So there's a large gap. This is 1,000 kilometers of ocean crust or something like that. Okay. So we're going to call this this area that's pretty shallow water, but we're going to call that the shelf, continental shelf. There's a part here where the depth of the seafloor is increasing. That's the slope, continental slope. And then there's the next area out is called the rise. So it's pretty deep, but not as deep as the abyssal plain. So a little bit of sediment, clearly sediment's making it out to the slope. Some is making it out to the rise. You maybe put a little bit there. The abyssal plain's pretty far away. Not much sediment's going to make it out from the continent. Okay, so then let's label this ocean crust. Label this mid-ocean ridge. And so the mid-ocean ridge would have, if you remember back to intro geology, it's going to have a mirror image. The magnetic stripes are going to be the same on either side. So the Atlantic margin formed by, it was a continent that split apart. And so this sequence of rocks kind of tells us that story. And we can count back in time on these magnetic stripes and sort of reassemble Africa and Europe with North America. And so this tells the story of that. Let's finish put some more ocean water here. So it tells the story of the development of a continental margin, a passive margin. Okay, so we can label. Put one more label on. So the platform and shield, we call this the craton. So the craton's like the pretty intact, it hasn't been broken up by faults, it hasn't been thinned. It's like the part of the continent that unaffected basically by the rift event. And we're going to go into exactly how this formed. But first let's put some ages on here. So these sediments are Triassic, so that's the symbol for Triassic. So Triassic's the earliest part of the Mesozoic. Triassic, non-marine sandstones and basalt. So that's interesting. They're clearly under the ocean now, but these formed above sea level. The oldest sediments we see here are early Jurassic. Upper parts of the sedimentary pile here are Cretaceous. We use a K for Cretaceous. Cretaceous to Cenozoic, and going into the present day. Okay, so how does this develop? We'll just leave that there for now. Development. Continental shelf section. Okay, so the first step is the onset of rifting. So we start with the continent. In this case, it was supercontinent Pangaea. And we've got continental crust, so it's just going to be crust, a lot of it potentially above sea level, at least the top part of it. So this is our symbol for sort of granite. And it's being pulled apart. Below the crust, we've got the lithosphere. Which is the pretty cohesive part of the mantle. Well, the Stenosphere is below that. So, yeah, the lithosphere includes, part of the crust and an upper part of the mantle. That's pretty cohesive, and then the Stenosphere is where it's kind of mushy and can flow very easily. Okay, so you start pulling on the continent, and you're going to, in that regime, you're going to start to form normal faults. So put some arrows on those. Okay, so normal fault. The first start is we're going to break. We pull on it. We start breaking it apart with normal faults, predominantly. Okay, and then we can move on to a second stage, which we call Continental Stretching. So now we're going to have those normal faults are pretty well developed. So this should look kind of similar to some of the things we drew when we were drawing the low angle normal faults, for example. Okay, so this continental material has been broken into chunks along faults, and you've deposited in these little low-lying areas sedimentary rocks, oftentimes conglomerates, coarse-grained continental material. And the lithosphere has been thinned. So this is we're still stretching this. So each of these is a normal fault. Okay, so these, just going back, so these faults that we've just drawn, these are going to be, these are these faults here that are going to end up being in here. I think we've drawn them the opposite direction, but they could form either direction. But so these are the sediments, the non-marine sediments that we end up with later on. Okay. So after this sort of stretching while remaining continental, so it's still not deep enough necessarily, or we haven't thinned it enough that it actually falls below sea level. Next, we're going to have what we call the rift drift transition. So this is, we're modeling this on the Atlantic example, but this is the pattern that we see any place that a continent is splitting apart. So Eastern Africa, Northeastern Africa has a place where it's like undergoing this currently. So we see this is one of the major tectonic processes that happens. Okay, rift drift transition. So here we have, zooming out a little bit, let's switch our normal faults back the way we had them up above. Here's our little sedimentary basins. We're zooming out a little bit, so here's our thinning continental crust, and then here we're out into new oceanic crust. And we deposit some layers of sediment on top of the continental stuff that we had before. We call this, we call this a breakup unconformity. You could put, there's going to be some layers there, but maybe we make it a little bit squiggled. Okay, so this unconformity goes over the continental material. It's marine. These are marine rocks. And it's probably better to not make it look like a pile. Right? It's maybe something like that, okay? So that unconformity is the one that we have up here. So this all along here is an unconformity where there's, a big gap in time, different amounts of time. Not as much above the sediments in these Triassic sediments and what's above them, but much larger unconformity where the new deposits of the Sedimentary Wedge are sitting on the old granitic rocks from the continent. And so that is how we form. That's the sequence of events that forms a sedimentary wedge on a passive continental margin. And you can get a sense of the time scales involved from the ages that are given here for the Atlantic margin. Okay. So next we're gonna talk about sort of the opposite setting where we have a convergent margin. And we'll use the example of the Western US Cordilleran origin. So an origin is a sort of a geologic collision, or place where things are coming together and pushing up, typified by thrust faults, although there will be all kinds of faults, of course. So let's just define orogeny. Orogeny is an elongate zone of lithospheric deformation occurring over a finite period of time. For example, modern California. Elongate zone of lithospheric deformation occurring over a finite period of time. So this definition doesn't really say necessarily it has to be convergent or divergent or anything like that. So we'll go with that. Although I think it's more typically applied to convergent places. Okay, so we'll start before the Cretaceous. So greater than 145 million years ago. And we're going to look at the western North America. So we're going to have a belt of rocks. I'm going to undo that. It's a little bit more like that. And then a kind of wiggly line, sort of like this, and then something like that. Okay. And this will be the Canadian border. And Mexico border is down here. So we're zoomed out pretty far. And so this would be the Pacific Ocean. We're going to define sort of three areas here. This will be area 1, 2, and 3. Write 3 a little better than that. Okay, so area 1 is accreted Paleozoic to Mesozoic rocks. Okay, so this is continental material now that has been accreted, means it's been kind of mashed on to the side to North America. It didn't used to be there before the Paleozoic or Mesozoic, but due to subduction and perhaps some strike-slip motion, bits and pieces have been mushed together and stuck on to the side of the continent. Next to that, in area 2, is passive margin sedimentary wedge. Okay, so this is a wedge of sedimentary rocks, just like the one that we described a bit earlier. So the western U.S. at some point, 600 to 200 million years ago, looked pretty much like the mirror image of what we see now on the East Coast. Thick, sort of 10-kilometer thickness pile of sedimentary rocks. And then area 3 is stable continental interior. So this is the craton that we identified before. So this sequence, this 2 to 3, we described that above. We could label this 3, and we could label this area 2, but we're on the west coast now. Okay, so we're looking at here in map view, and we call this area, this boundary between the passive margin sediments and the craton. We call this the Hinge Zone, and you can see that, up here. This would be the Hinge Zone right here. So where it goes from pretty thin, and then you got all the sediments, and the older granitic stuff is thinned out as well. Okay, so the area that's going to become, this is the prelude. This area is going to become the Cordilleran origin. So this is the future. So this is going to get turned into this elongate zone of deformation. At this point in time, before the Cretaceous, it's pretty peaceful there. Except for the events where stuff is accreted. We're not going to get into that right now. Okay, so one major part of the Cordilleran orogeny is a sort of a sub-orogeny called the Lair orogeny. This occurred from the late Cretaceous to around 20 million years ago. All right, so here, this is going to kind of look, we're going to draw those same sort of belts of rock. All right. So this line here is the hinge we drew before, and it's going to be associated with thrust, a lot of thrusting. So we're putting thrust teeth along the hinge. We could actually go back to this plot as well. We should have put teeth on here, because the accreted stuff is basically thrust onto the passive margin. Okay. Sorry about that. All right. So back. Okay. Start with that setting. So this is our starting condition here. And we're going to turn the hinge into a zone of thrusting, and we're going to label some different areas. So shade in this one we'll shade that in with sort of granitic hatches. Label it B. I'm going to put another line here. This is going to be, put some teeth on it. I'm going to call this area A, and we'll call this area C. Okay. So what are these areas? So area A is the accretionary prism. Or the subduction complex. Okay, so we still have this along the parts of the West Coast, for example, in the Pacific Northwest. We have volcanoes, Mount St. Helens, and there's a subducting ocean crust going down under a eastward dipping subduction zone that's labeled A. And so in this area of A, we get what's called an accretionary prism. And let's just kind of draw that. Okay, so this is sort of review from Geo 101, but so here's area A, ocean crust being subducted, and we're going to scrape off some material in a sort of wedge shape. So this is the accretionary prism. And then over here, we've got our volcanoes, right? Okay, so the material is scraped off the downgoing slab. This would be our area B. There's granite underneath the volcano. So these are our areas A and B. Let's say what B is. B is the Mesozoic volcanic arc. And C is what we call a foreland fold thrust belt. So it's an area with lots of folds and lots of thrust faults, and occurs fairly inboard, fairly far away from the coast, from the inland from the volcanic arc. And this arrangement is all superimposed onto the what we have here. So the hinge zone. It turns out that these sedimentary rocks, past the sedimentary wedge, are very easy, pretty weak compared to the granites underneath, and they get pushed on top of each other, faulted, folded. They turn into this foreland fold thrust belt that we had down here. And then this volcanic arc sort of cuts across both the accreted rocks and some of the sedimentary wedge as well. So I should probably label this. Let's label this last line here. This is the coast. Okay, so it was figured out in the 1960s that this arrangement, so this is what This is what we see now. We see this is the Sierra Nevada and other granitic rocks when you go out west. We find the Subduction Complex, which is the most famous example being the Franciscan rocks in California. And then you find all these folds and thrusts to the east of that. So this arrangement of these sort of three styles of geologic activity, this looks like the modern day Andes. So if you go down to South America, we have the volcanic rocks. We have active faults and folds. In the western U.S., these thrust faults aren't active anymore. So what we don't see in the Andes, though, is this accretionary prism, partly because it's either underwater or sometimes the rocks aren't actually sometimes these sediments just get sucked down. And potentially they get sort of glommed on to the base of the crust, or they go further down and they get melted and end up in the volcanic rocks. So just to wrap this up, what happened since 20 million years is that the plate boundary changed and this area actually went under extension. And this is how we formed the basin range. I mentioned earlier in the class that states like Nevada used to be half the thickness that they are now. So during this time when there was compression on the west coast, it kind of pushed things up, high elevations, thick crust, and then when the plate tectonic setting changed and you end up with the San Andreas Fault and you're not pushing so hard on the continent, this area spread out, thinned, normal faults, low angle normal faults, basin range. Okay, and that's where we'll stop for today.